In the electrolysis of molten salts, there's only two ions present. The positive ion or cation will be reduced at the cathode, and the negative ion or anion will be oxidized at the anode. In the electrolysis of aqueous solutions, there's multiple species present. Some are preferentially reduced and others oxidized. Things that can affect that selection of what reaction takes place involve things like what's the value of the standard electrode potential, what are the concentrations of the ions, and what's the nature of the electrode. And we'll look at that in part 2 of these videos. A generic approach we can use to attack these problems first begins with identifying the positive species and water. They will both migrate to the negative electrode. There they will undergo reduction, and the reactions for these are in our IB data booklet. We select the one with the higher potential. The negative species and also water can migrate to the positive electrode, and there they can lose electrons and undergo oxidation. These reactions are also in our IB data booklet, but we need to reverse them to represent oxidation and select the one with the higher potential. Let's put these steps in action by looking at an example of sodium bromide. So first of all, at the negative electrode, it would attract the positive sodium and our ever-present water. These two reactions we can identify in our IB data booklet. Both of them written as reduction potentials, gaining electrons. So I'll copy them both out. And now I select the one with the higher reduction potential, which would be that one. Remember, these are negative numbers, so negative 0.83 is a higher potential than negative 2.71. At the positive electrode, our bromine would migrate because it has a negative charge, and our ever-present water. I identify the reactions for these losing electrons, hence the reverse direction. And these I've shown in the green down below. I'm going to write out those reactions now. However, I'm going to reverse them. When they're reversed, their sign of the reduction potential also is reversed to represent now oxidation. So which of these two is a higher value? Well, the bromine. So visibly what I would see happening is the formation of bromine liquid at our positive electrode, and if you had some sort of indicator present, you might notice the presence of the hydroxide ion at the other electrode. Let's go on to the electrolysis now of a copper chloride solution, and in particular a dilute one. So starting off at our negative electrode, our positive ion would migrate in that direction, and our ever-present water. Identify these two reactions from our IB data booklet. Here they are, both gaining electrons, which we want happening at the cathode, where reduction always occurs. I write out the two reactions. I identify the higher of the two. So I would see the formation of copper at the negative electrode. At the positive electrode, I would have the chlorine ion migrating in that direction, and again our ever-present water. And now I'll identify those two reactions with them losing electrons. Remember, I need to write them in the reverse direction. So there's the chlorine losing an electron, and here's the water losing an electron. I identify now the higher of the two, and so in a dilute solution of copper chloride, I would see the formation of copper at one of the electrodes, and at the other, the formation of oxygen gas. Now consider what would happen if we were to use a concentrated copper chloride solution. Concentration can override the electrode potential when the potentials are close to each other. So in our case, the negative 1.36 and negative 1.23 are somewhat close, and if I have an excess or an abundance of chlorine, it's possible then that the chlorine will undergo a reaction. In our example so far, the electrodes have been inert. In part 2, we'll explore when that's not the case.